So without further ado, let's get started. I'm going to open up the questions. While we are getting the questions live and good to go, there's been a kind of a question about the content, or not the content, the points of the exam and where all those are coming from. So with the exam is 45 points. There are no short answer, or sorry, there are no multiple choice. It is all short answer. Now, MRS and I, we would not give this exam to you if we didn't feel confident that you can do it. Additionally, in this exam, there is 3 points of extra credit. So those points are available for you, and everybody will be getting 60 minutes unless you have already approved accommodations. So with that in mind, let's get started. The first question on here is going over calorimetry questions, specifically the negative Q metal is equal to the positive Q of water. So for that, the negative Q of any metal, right, any heat that's lost by a metal when it's placed into water will be gained by that water, or gained by the surroundings. So, or in other words, negative Q metal is equal to positive Q water. So say, for instance, we have this cup of water here, and I put this red hot piece of metal in it. The metal will cool down while it warms up the water. Or in other words, any heat gained by the water is lost by the metal. Now, of course, with this equation, we can also translate this to Q, because any Q is equal to MC delta T. Oh, sorry. MC delta T. So we can actually substitute this in for the Q metal and the Q water. Observe. We'll use pink for the metal. So we have the negative mass of the metal times the specific heat of the metal times delta T of the metal. Now this, of course, would be equal to, we'll use blue, of course, for water, the mass of the water, the specific heat of the water times the delta T of the water. And they'll equal out. The reason why they equal out is because delta T for the metal is going to be negative. So negative times a negative, of course, is a positive. Let's do an example. Rather than write out an entire question, I'm going to just put values in here. So let's say our question says the mass of the metal is 100 grams. Let's say we don't know the specific heat of the metal, but we do know that the delta T of the metal is, let's say, negative 36 degrees Celsius. Now, again, all this information would be given in a equation, or sorry, in a word problem. And let's say that the mass of the water, let's say, is, I don't know, 75 grams. Specific heat of water, which is given on the exam, is 4.184 joules per gram degree Celsius. And let's say delta T is equal to 4 degrees Celsius. 4.0, sorry, degrees Celsius. Now, all we do with this, right, we've got a lot of values here, but the bonus of this is that we've already got them sorted. So all we just need to do is plug them in. Observe. We've got the negative 100 grams times C metal times negative 36 degrees Celsius. Now, of course, this is equal to, we've got 75 times 4.184 times 4. And after this, it's just algebra. Right? That's all we're doing here. We need to isolate the specific heat of metal in this case. So the first thing I'm going to do is multiply the thing on the inside of the parentheses. So we've got the negative quantity of negative 3600 times times CM. And this is equal to 75 times 4.184 times 4. Now, of course, these negatives will cancel out. 2 negatives make a positive. So to isolate CM, we just divide both sides by 3600. So we pull out our handy-dandy calculator. We got the fraction of 75 times 4.184 times 4 divided by 3600. And we get that this metal has a specific heat. So this equals Cm, which equals 0.34866 ... But when we round to sig figs, looks like we've got 2 sig figs we need to round to, 0.35 joules per gram degree Celsius. Don't forget your units in your equation as well. And that would be our final answer. So once we, kind of hit that unanswered, sorry, just sorting out the questions here for calorimetry. The next topic here is, can we go over serial dilutions? Sure. So serial dilutions, all that means is one dilution after another, after another, after another. So all you do for this, for serial dilutions, is the equation that's tried and true. M1V1 is equal to M2V2. Let's say this. We've got a starting solution that has a molarity of, let's say, 12.5 molar. Let's say solution A is made by diluting 14 milliliters of the starting solution to 140 milliliters. Solution B is made by diluting 36.7 milliliters of solution A to, let's say, 73 milliliters. And finally, let's say solution C is made by diluting, let's say, 14.3 milliliters of solution B to, let's say, 150 milliliters. What is the concentration of solution C? So that's our question of the day, right? There's a lot going on here, but we got to just start at the beginning and work down. Let's start at the top. I'll leave this up here for just a second, so anybody who would like to take a photo of it can before we get started. All right, let's do this shindig. So let's start up here. Solution A is made by diluting 14 milliliters. Okay, so that's going to be our starting volume, V1, of the starting solution. So that means this here, oh, we'll use blue, is M1 to 140 milliliters, or V2. With those in mind, we can now take this over here of your M1V1 is equal to M2V2, where we've got 12.5 molar times 14, right? 14 milliliters is equal to, oops, sorry, 140 M2. Now, of course, how do you isolate M2? You divide both sides by 140 milliliters. Your milliliters cancel out. So you bring out your handy dandy calculator, 12.5 times 14 divided by 12.5 times 14 divided by 140. And we get that solution A is equal to 1.25 molar. This is great. Give yourself a little pat on the back, right? You did a good job. Let's zoom out. Now let's take a look at this. Solution B here is made by diluting 36.7 milliliters. So that, using a different color, this is V1 of solution A. Now, when it says solution A or solution B, it's referring to the molarity you just calculated. So when it says solution A here, it's really referring to right here, that molarity. So this molarity is M1. M1 V1, and this here, 273 V2. So again, all we calculate is molarity of solution B. In this instance, that would be 1.25 times 36.7 molar milliliter is equal to 73 milliliters times M2 to find molars. Divide both sides by 73 milliliters. And bring out your handy dandy calculator. Everybody should keep a calculator by their computer, right? Imagine all the learning you're missing out on if you don't have it next to your computer. And we get this equal to 0.62424 right, molar. Now I'm saying ... because it goes on for quite a long time. We're going to leave it unrounded for now. We'll round at the very last step. So the real question is, am I done? No, we aren't. Because we're only at solution B. We need to get to solution C. So that means, of course, time for a new color. We have solution C is made by diluting 14.3 V1 of solution B, M1, to, this is 150 milliliters, V2. We just plug them in. 14.3 milliliters times 0.6284246575 is equal to 150 milliliters times M2. Forgot to add my molar to this. Divide both sides by 150. And so we get answer times 14.3 divided by 150. And we get this concentration of C is equal to 0.599098174 molar. Rounding to sig figs. I'm sorry, there's a 0 right there. We get 0.060 molar. The reason why we use 2 sig figs there is because, well, a couple reasons, right? A couple of our numbers here have 2 sig figs. That'd be the 73, the 150. So again, the lowest number of sig figs is what kind of calculates the number of sig figs. We'll leave this up here. This will also be available. We'll post it. If you're in my classes, you will post it into the Schoology here at the end of the call. Quick coffee break. Coffee's delicious. Can we go over, will we ever need to find kilojoules? That's a great question. Kilojoules, referring to heat, is all about, when we talked about joules is a SI unit. So all that means is that it's subject to metric conversions. For instance, right, let's say you got for some final answer, I don't know, 1,501 joules. What that would be in kilojoules is, of course, 1.501 when you move the decimal point 123 spaces over, kilojoules. So that's really the only thing that you would need to use it for. But the question that's after is a very, very good question. The question is, if we have a Q is equal to MC delta T, how can we find the final temperature? So, good question. Let's say, for instance, that our heat gained by this object is, I don't know, 15,047 joules. The mass of some metal, let's say, is 143 grams. Let's say the specific heat of the metal is 0.450 joules per gram degrees Celsius. And let's say we only know our initial temperature. T initial is equal to, let's say the initial temperature is, we'll just go safe, 22.7 degrees Celsius. Now, we need to find T final. So with this equation here, when we have Q is equal to MC delta T, this delta T here, we can split up into two things. Or in other words, we can rewrite this equation to Q is equal to MC times T final minus T initial. That now we can plug things in. 15,047 joules. You have been maybe noticing as well that I've been putting units in everything. It is a good practice to have. I would highly recommend it for the exam. 143 grams times 0.45 joules per gram degree Celsius times T final minus, what the heck did we say? 22.7 degrees Celsius. And all we do at this point is solve for T final. We divide both sides by 143 grams times 0.45 joules per grams degrees Celsius. And we get, using our, of course, handy dandy little calculator, 150, the quantity of 15,047 divided by 143 times 0.45. Ooh, there's a large temperature change. Anyway, we'll run with it. We'll say this is the temperature change would be 233.83061338 degrees Celsius is equal to T final minus T initial. Now, at this step, we like to round. So we look at the least number of significant figures from our givens, from these three givens specifically. So we get 233 degrees Celsius is equal to T final minus the 22.7 degrees Celsius. So we add 22.7 degrees Celsius to both sides, 233 plus 22.7, and we get T final is equal to 255.7, which rounds to 256 degrees Celsius as your final answer. Will the extra credit be from this unit? No, the extra credit is fair. Anything from semester 2 is fair game. Can we go over reading a solubility graph and what temperature does to a liquid versus a solid? Great question. So this question is really more particularly designed for my class versus MRS's class, because my class will have a solubility graph on their exam. We will go ahead and get through this question really quickly to keep this session approachable for everyone. So a solubility graph has a bunch of different lines, right? We've got a line here, we've got a line, in a different color, Sally, something like this. We've got some ones that's maybe going way up really quickly. We've also got some going, way down, right? Bunch of these things, right? If you have something, right? So if the points that you plot is below the graph or below the line, let's say we're looking at this pretty pink line here, is below the line, it is unsaturated. If it's on the line, it is saturated. And if it's over here on the left side of the line, it is supersaturated or above the line. That's really all it is. Here, there is another big difference that I'd like to point out. We'll use yellow. Solids, as temperature increases, the solubility for solids go up with it. But for gases, they go down. Now, I'm sure you can predict what can happen for temp going on the opposite direction, temp going down. Solids, gases. As temperature goes down, gases go up, solids go down. So a good way to remember it, solids always stick with the temperature, gases go against it, because gases like to be their own thing. Hi, can we pretty please, why is there three pretties, go over potential energy diagrams? I have no idea what's going on. Sure, we absolutely can. This question is also a very good one for MRS's classes, because I know you have a much more in-depth potential energy diagram that you go over. So a potential energy diagram. It's a graph. On the left side, the y-axis, this is usually in joules or kilojoules, right? This is energy required for it. Specifically, it's called potential energy. That's why it's called a potential energy graph. Down here, we've got, right, or the reaction pathway that it takes. There's two versions that you can see, or you will have to draw. The first version looks something like this. Let's talk about this one first. This here is a endothermic graph. The reason why it is a endothermic graph is because the starting point is below the ending point. In a more technical definition, the reaction gains energy over the course of the reaction. Now, particularly in MRS's class, you are going to be responsible for determining the activation energies and the enthalpy changes in them. And a couple other things from what I remember. I don't have the exam next to me this time. To calculate the activation energy, or that'd be EA, all you do is go from the top of the crest to the bottom. So you're looking for this change here. Right, that's your activation energy. Your change in enthalpy, on the other hand, or delta H, is your difference between here and here. Again, all of these is final minus initial. Final minus initial. You always go from final minus initial for any of these. For a exothermic graph, again, kilojoules, this is where it's a crappy exothermic graph. Ooh, say something like that. Looks good to me. This should be exothermic. A exothermic graph, we know that it is an exothermic graph because the starting point is above the ending point. On a more technical definition, the reaction loses energy as it goes through. Your EA is smaller this time, right? This would be your EA here. And your delta H would be that one. So this would be your delta H, and this one would be your EA. How many questions exactly are on the exam? I couldn't tell you. I think it's 9 or 10. Let me look right now. I'm also using this as an excuse to drink some more coffee. So both exams have 45 points. However, my class, there is 9 questions, not counting the extra credit. And in MRS's classes, there are 7 questions, but you've got a question with a decent chunk of parts. But again, neither exam is harder than the other. We've designed both of them to be the same difficulty. So just because MRS's classes have 2 less questions than my classes, still the same number of points. And it's the same number. We each have the extra credit question that's going to be there to help you as well. When using sig figs, can you discuss can you describe, this question's worded a little bit awkwardly. Can you clarify when to use sig figs based on the numbers in the equations versus the numbers when doing temperature change? Good question. For your sig fig calculations, you need to handle each type differently. Right? If you recall, right, multiplication and division use the least number of sig figs versus the adding and subtracting use the least number of decimals. Now, that is important at that point because the only time that we've seen this kind of really come up is when we're doing these heat calculations. So whenever I'm doing these kind of heat calculations, I like to do our delta T first. Try to find that first and round to appropriate sig figs at that step. Then we can use our Q is equal to MC delta T to then figure out the rest of the equation. Then you use the sig figs from the equation and the sig figs you got from your subtraction. What if you have to find Q in calorimetry? You won't have to find Q for this exam. Even if you wanted to find Q for calorimetry, if we go back up here, where was it? Up here. All we do is just do that one equation, and then we get Q. That's how we find Q in calorimetry, is really how it is. It's the easiest way to find it. I'm aware there is a backlog of questions. We are getting through them slowly but surely. We went over endothermic graphs. Is a stock solution the same thing as a starting solution? Yes, yes it is. If you have the final and initial temps and you have the change, can you use the change in temp for sig figs or only the sig figs from the final and initial temperatures? So from that idea, you want to calculate your delta T first, round to appropriate decimal places, then use that number of sig figs. How many sig figs should we round to for each answer during the multi-step problems? Personally, and MRS is the same way, I believe, we like to use the unrounded answers all the way until we must use the until the last possible step. Like even if you see here, we use the 0.6284 and change to get our final answer, and then we round it. When solving for dilutions, can you only use molar, or could you use millimolar or something else as long as it stays consistent? We would prefer answers to be in molar just to kind of keep it nice, easy for everybody to understand. However, if you give a question in millimolar or kilomolar for some reason, as long as it's correct, it should be good to go, but I would talk with your instructor before doing it. A good recommendation is that you just stick with molar. Do we have to add units into the work or just the answer to get credit? Adding units to work, you have to look at the directions on the exam. I believe the exam directions state that you must show units at every possible step. Now, I know that's a not fun thing to do. It is a good practice, though. Right? MRS and I have seen on many occasions that students lose points because they don't use the appropriate units in their equation. Right? They don't use their appropriate things in that equation. Now, so I'm looking at the exam right now, right? In the directions, it says complete all questions to the best of your ability. When applicable, do not forget to show work, include units in both your equation and final answer, and round to the appropriate number of significant digits. Good luck. So with that, you need to have units. Will they tell you what units to use? No, or what units to be, yep, you all are right, you're right. Most questions will say like, how much heat is required? Or what is the molarity? Or what is the specific heat? So using those ideas, you can be good to go from there. A couple people who have pointed out a error in one of my things here. And I see it. Me scroll way down through my answered questions. Isn't there 2 sig fig 0.45? No, it would be, the question was here. It's 0.450. That's why. 3 sig figs. $140. Yes, I know my battery's low. Anyway, I'm not sure where I'm seeing this 140. In any case, let's keep going through these questions. Oops, sorry, unanswered. Can we do more negative calorimetry problems? Good question. And yes, we can. Negative calorimetry problems. Is that more relating to just like doing more examples of calorimetry or doing more examples of where Q would end up negative in your answer? So I'm going to assume it's doing Q where we have a negative Q, and we need to find the change in, let's say, change in temperature. Let's say we've got Q is equal to MC delta T. Let's say our Q, a Q, of course, heat, can be positive or negative. Let's say Q is negative 8,090 joules. Let's say the mass of this mysterious object is, I don't know, 150 grams. Let's say we're trying to find our specific, or let's say our specific heat. We'll say this is water, 4.184 joules per gram degrees Celsius. Let's say we're trying to find delta T. What is the change in temperature? Negative 8,090 joules is equal to, what did I say, 150? 150 grams times 4.184 joules per gram degree Celsius. We'll move this over. Times delta T. So we just divide both sides by 150 grams times 4.184 joules per gram degree Celsius. And we get negative 8,090 divided by 150 times 4.184. And we get negative 12.89 degrees Celsius is equal to delta T. Rounding to sig figs at this stage, there are 3 significant digits. In our lowest number that has significant digits, 12.9, negative 12.9 degrees Celsius is equal to delta T. Will Mr. Booth's class have potential energy graphs? You may be required to draw. For Mr. Booth's class, you will not need to calculate delta H either. You will not. For MRS's class, I believe that is fair game. Are you going to have to write the definition for a solution? Probably. It's a good bet. What's the equation in neon green again? There's a couple in neon green. Is it this one? Here, this one? That's just your change in enthalpy. Will we have to define solute, solvent, solution, supersaturated, saturated, and unsaturated? You will probably need to use them in like a sentence or a scenario, or create a solution, create something that's saturated or unsaturated or supersaturated. So keep those in mind. What was that thing you said before the last quiz about check the wording of Q in the word problem? Like it said 200 joules are absorbed or released. Aha. So on the exam, you don't need to worry about that wording specifically. Basically, if heat is released or energy is released, it is exothermic. If energy is absorbed, this endothermic changes to negative. Will we need to change the final answer to negative or positive depending on if the reaction is endothermic or exothermic? Your math, when you do your algebra, should leave it pretty good. So I don't think you need to change anything. If you get a negative answer for mass, would it make sense to just make it positive? I would check your math for your, how you say, make sure you didn't lose a negative one. So. How would you create a solution for something that is unsaturated, saturated, or supersaturated? So perhaps first, let's go over what is a solution. Right? What is this thing? Before we dive into it, quick water break. Sorry, pulling up the exam to make sure we're getting the right data. So a solution, right? All a solution is, this is a homogeneous mixture where a two or more substances is dispersed. Right? Those two substances, of course, are a solute and a solvent. To make a solution, you will always mix either solid in a liquid or liquid in a gas. Clear, clear. Now, to make a solution unsaturated, right? A unsaturated solution, right? If you look on a solubility graph, is something that is below the curve, right? Something that is here. That all that means, unsaturated, means that you can add more solute. You can add more solute and it will still dissolve. That's a key point there. And it will still dissolve. When something is saturated, right, if you're looking at a curve, right, they'd be on the line. You cannot dissolve more. Kind of like if you put too much Kool-Aid mix into a cup of water, it'll kind of make a pile at the bottom and it won't do anything. To create a supersaturated solution, or if you're looking at a solubility graph, it would be over here. You cool down a hot solution that after you cool down that hot solution, right? Let's say you had it was right here unsaturated, but as you cool it, it turns into supersaturated. So that's how you would create it. Solvent is the thing that the solute is dissolving into. So let's say if you've got a beaker, the beaker's green today because I say so. We've got water. We've got some salt. I know, I should be an artist. The water is the solvent. The salt is the solute, right? The salt is dissolving into the water. Can we go over Q metal, Q water again? Yes, I'd like to go over a couple of these other definitions before we get going into one more math problem for the day. How can you solve for the saturation point? On a graph, all you do is you figure out how many grams it has and what temperature. That's it. To solve for the saturation point at a specific temperature, you just make a note of where the temperature is and follow it up until you cross the line. Do you need to use, well, MRS's class need to use unsaturated and saturated, miscible dilution, stuff like that. Yes, you will. It's probably a good idea to have those down in your vocabulary. For creating a solution, would we be given a graph and have a temperature and say what could be saturated at X degrees? If you are creating a solution, you will not be given a graph. But if you are making, let's say the question says how would you make a solution for this? Then you can describe the process. Will you ever have to create a solution or find a saturation point without the graph? We just covered that. How can you create a solution without a graph? So this is more going down a good rabbit hole, and I'm happy to kind of discuss it. Let's say a good example is perhaps one of the questions on the exam says, how would you make a saltwater solution for, your fish, your saltwater tank? So all that is that you can take a look at the graph. You say we'll take a look at the graph. We'll see how much salt I can dissolve into this, how many gram water. If I put this much in, it'll be unsaturated. If I put this much in, it'll be saturated. And if I put this much in and then cool it down, it's super saturated and concentrated, and the salt's acting as a strong electrolyte. That's really the extent of that question, if there would be one like that on the exam. Would you say this this exam is more math-based or more definition based. I'd say more math based, 100%. But how do you create a solution without having a graph? The question, I don't want to give too much information about that type of question on the exam. That type of question is saying, like, create a scenario where you would need to make a solution. Then you can describe how you make the solution. So really it's a solution that you make up. If you have any other questions about that specifically, I recommend that you reach out to me via email. To finish off the review session, we're going to go ahead and call the line for questions here. The last question, partly because it's almost time, the last question that we would like to go over is the negative Q metal is equal to positive Q water. So all this is, right, let's say we've got this really red hot piece of metal. Now this really red hot piece of metal, we take our cup and we cool it down. The heat that's lost by that pen, or the metal in this case, is gained by the water. And that's what that equation's telling us. Right, so if we go way up here, up to this one, right here, we've got the negative Q metal, which is here, the positive Q water here. So whatever heat the metal lost is then gained by the water. That's really all it is. We'll take this pen out. With that, it's actually 9 o'clock. I hope this review session was helpful. If you have any further questions, you want clarification on things, I highly recommend that you reach out. The email is sboos@dpaulprep.org. I'll be up for probably about a couple more hours, so I'll be next to my computer with email access in case if you all have any questions. Again, thank you all for coming. I really do appreciate it. Can you zoom out real quick for a screenshot? I'll actually do one better. I'll upload it to Schoology. For MRS's classes, I don't know if she how to post this on your guys' stuff, so I'm going to go through this very slowly, just in case if you want to take extra screenshots. So we'll leave this here. I'll even give a little thumbs up. Okay, next. Okay, next. And last but not least, this one. Oh no, actually, sorry, there's one more. The best thing you can do for this exam to prepare is to review your notes, review any past materials your teachers have given out, get a good night's sleep, eat a good breakfast. You guys have got this. We believe in you.